Hello, students. This is 12.2, which is about chords and arcs. Ideally, in the classroom, the way this would work is we'd do this over several days, and we would take time to look at each of the theorems and prove them. And at that point, you would have your homework to do. We don't have that luxury right now. So what I'm going to do in this recording is quickly go through the theorems, describe them for you, tell you what they are, and then give you the applications. And then my plan is to put out another video in which we go through the proofs for these theorems, because the thinking process for these theorems is just as vital as learning them and how to apply them in terms of what I want you to get out of geometry this year. But to start off with, we are just going to do the practical so that you are able to accomplish the assignment that is going to be due on Wednesday. Okay, so 12.2 is about chords and arcs. And we have several theorems to look at. First of all, you need some vocabulary. Remember that a chord is a segment whose endpoints are on a circle. Okay, so theorem: within a circle or congruent circles, congruent and central angles have congruent arcs. We've talked about this already, right? So we'll just give ourselves a circle. And if you want to just follow along in your book, those are the theorems that we're going to be talking about today. So you can see where I'm going, where I'm starting and where I'm going to. Okay, so within a circle or in congruent circles, congruent central angles have congruent arcs. Okay, that's one of them. Okay, the other is congruent arcs, congruent central angles have congruent chords. So we're going to do both of those together. So within a circle or congruent circles, congruent central angles have congruent chords. Okay, so what does that look like? So let us take these two chords, two central angles, and we're going to make them equal to each other. Okay, so A, B, C, D, and we have circle O. All right, so in this triangle, or in this circle, sorry, if angle AOB is congruent to angle COD, then the measure of arc AB is equal to the measure of arc CD. And the two segments are also congruent. And AB is congruent to CD. So those are our first two theorems. Next, within a circle or in congruent circles, congruent chords have congruent arcs. Now, that kind of follows from the first one that we just did. So So in this circle, if we have two arcs, two chords that are congruent, then the arcs that they cut off will also be congruent. So I'm making my two chords 2 inches long, making them 2 inches long. So this is congruent to this, and so that means that the arcs are also congruent. Congruent chords, cut off, congruent arcs. So if AB is congruent to CD, then arc AB is congruent to arc CD. Right, the converse is true too. If two chords are congruent, if two arcs are congruent, the segments are also congruent. So if AB, arc AB is congruent to arc CD, then segment AB is congruent to segment CD. Okay, next. This one's interesting, and I love going through the proof for this one, which we will look at. If two chords are equidistant from the center, then they're congruent to each other. So if I take a chord and I determine its distance from the center, so notice I'm doing a segment that's at right angles. So that was 1 inch. If I draw a chord in another place that is also 1 inch from my center, it will be the same length. So E, F, A, B, C, D. So the converse is also true. Okay, so within a circle or a congruent circle, chords are equidistant from the center or centers if and only if they are congruent. I'm going to put the converse, the original and the converse in there together. Chords are congruent if and only if, that's IFF abbreviated, they are equidistant from the center or centers. So in this case, that means if EO is congruent to FO, then AB is congruent to CD. Also, if AB is congruent to CD, then EO is congruent to OF. I need to put my perpendicular signs here. Okay, got our right angles. Okay. We have 2 or 3 more theorems that we want to look at. Okay, the next one has to do with diameters. So if we draw a diameter and that diameter is perpendicular to another chord within the circle, remember a diameter is a special type of chord within a circle, then it's going to bisect that chord. So if I have a diameter and it is perpendicular to a chord, it bisects the chord. So this diameter is perpendicular, and therefore these two are congruent. Okay, so if this is in a circle, or congruent circle, no, we're going to say, we're going to do the if and only if. A diameter is perpendicular to another chord if and only if it bisects the chord. So if AB is a diameter and AB is perpendicular to CD, then CP is congruent to DP. If CP is congruent to DP and AB is a diameter, then AB is perpendicular to CD. So there is that theorem, those two theorems. All right, the last one is just an extension of this one, right? It is the perpendicular bisector of a chord contains the center of the circle. So the perpendicular bisector of any chord contains the center. Why is that true? Well, if it's the perpendicular bisector, this up here has to be true, right? Perpendicular bisector, perpendicular bisector. And the diameter, of course, is the chord that contains the center. The perpendicular bisector of a chord contains, we don't need a comma there, the center of the circle. So another way of saying that up above is if AB is the perpendicular bisector of CD, then AB contains the center of the circle. Okay, there are a few example problems on here that I want to look at with you. So first, problem one. Problem one is about using congruent chords. Okay, congruent chords. In the diagram, circle O is congruent to circle P. Oh dear. There we go. Apparently, my compass does not want to make two small circles. Okay. All right, circle O, circle P. And angle O is congruent to angle P. Oh, no. What do we want to do? We want to draw two congruent chords in these circles. Nope. Okay. Circle O is congruent to circle P, and BC is congruent to DF. What do we know? Or what can we conclude? Well, we can conclude something about these angles, right? Because congruent chords cut off congruent angles and congruent arcs. So we know, okay, first we know that the measure of angle O equals the measure of angle P. We also know that arc BC is congruent to arc DF. I'm intentionally switching back and forth between measure of and congruency because we know that those two things are interchangeable because of the definition of congruency. Okay. What else do we want to look at? We want to look at problem 2. And problem 2 is about the length of a chord. Okay. We have circle O, and we have two chords. We have PR and SR. Okay, so in our figure, we have these two are congruent. And we know that this is 12.5. We know that this is 9 and this is 9. So what else do we want to say? What's the length of RS and O? So this is RS and this is P. All right. So we want to know what is the length of RS? Well, first of all, we know that PR, because let's put a Q here. PQ has to be congruent to QR. And so that means that PR, which is going to be equal to PQ plus QR, to be by segment addition postulate, must be 12.5 plus 12.5. And so that's going to be equal to 25. Now, we know that PR has to be congruent to RS. Why do we know that? We know that because the chords are equidistant. They're 9 units away. And so that means that RS must equal 25 units. Okay, let's see. Okay, let's do problem number 5 now. Maybe we'll do a new piece of paper. All right, finding measures in a circle. What's the value of each variable to the nearest tenth? Okay, so let's draw our circles. Okay, so this is our circle K. Okay, this is 3 centimeters. This is R, and we know that this entire thing is 14 centimeters. And then we have N, M, and L. All right, so how can we find R in this picture, in this figure? Well, since Kn is perpendicular to Lm, we know that Ln is congruent to Nm. And since Lm is equal to 14, we know that Ln has to be equal to 7. Right? Okay, so now we just need the Pythagorean theorem. We know that Kn squared plus Ln squared has to equal Lk squared. So 3 squared plus 7 squared equals R squared. 9 plus 49 equals R squared. 58 equals R squared. We take the square root of that, and we get approximately 7.6. Okay, let's do another example. Okay, we have circle B, and in this circle we have E, and then all right, so we have that this is 11 and this is 11. We want to find Y, and this is 15. So how can we find y? Well, 15 is the radius. Because, that's one important information, because these two, we have, let's put some letters here, A, C, and F. Because AC is congruent to CF, that tells us that BC is perpendicular to AF. So we can add in the fact that this is perpendicular. Now, since 15 is the radius, we can draw in a more helpful radius, and we will know that it is also 15. So now we have a right triangle. AC squared plus BC squared equals AB squared. So 11 squared plus y squared equals 15 squared. And then y squared is going to be equal to 104. Y is going to be approximately 10.2. Okay, so that is what I wanted to go over with you for this unit. Your homework will look like solving problems using each of these theorems that we've worked through. So I look forward to seeing you in class soon.